Okay, so the next speaker will be Peter Goten. And as you know, he was not able to come because of COVID, but well, we thank you because anyway, you have made the effort to give the lecture by internet. So he will talk about the components of G-Higgs bundles, G-Higgs bundle moduli, and the Cayley correspondence.
Thank you very much, Tomas, and thank you both, Luis and Tomas, for organizing the conference and for inviting me to speak. It's really a great pleasure and honor for me to speak in a conference in honor of Oscar. I'm very sorry that I can't be there with you, but it was just not possible. I didn't recover in time. So I'd like to just thank Jacques for stepping in at short notice and taking over my slot on Monday. I certainly at that time wouldn't have been able to do any kind of talk. So thanks for that, Jacques, also. And also thank you to the organizers for making it possible to follow things on the internet, so that I've been able to see most of the talks and catch up with things on YouTube. So that's been really nice, given that I couldn't be there. So before starting my talk, I'd like to add my tribute also to Oscar. So I've known Oscar for very many years, since that famous Durham Symposium in 1993 that already Steve mentioned. So for quite a long time. So it's been a privilege. Oscar is one of my best friends, and I've collaborated with him and discussed lots of mathematics with him over the years. Had many inspirational discussions about mathematics and many other aspects of life, in fact. And we've shared many nice moments. Also, Oscar is a man of course, wide interests and talents and abilities, and some of them have already also been mentioned. So let me just show you here two pictures. On the left, Oscar's about to have one of his favorite meals, and on the right, that's the announcement of a concert we organized in Porto a few years back in 2018. Where Oscar was singing, so that was a very, very enjoyable occasion also. So yeah, so happy birthday, Oscar, and I hope to see you in real life soon again. Okay, so let me get on with my talk. So here's the title, as you see. What I'm going to talk about is basically taking as my organizing principle for my talk is how to count connected components of the moduli space of G-Higgs bundles, and I'd like to give you at least a conjectural answer to the problem. So maybe before, well, let me just start with setting up the. Let me just start with setting up the notation. Of course, you have seen some of this already during the week, but anyway, let me just to fix notation and to fix ideas, just quickly introduce the objects. So let's take a real reductive lead group G. It'll be connected at least most of the time. Maximal compact subgroup G. We get a cation decomposition, and this maximal compact. If you restrict the joint action, it acts, that decomposition is a decomposition of H modules. Okay, so what's the G-Higgs bundle on a Riemann surface or algebraic curve? It consists of a pair of two objects, a principal HC bundle, E, and this Higgs field, which lives in, it's a holomorphic one form, and it takes values in the MC part, so the complexified part of the joint bundle, but the part which corresponds to M in the cation decomposition here. So that's the idea. Okay, so these are G-Higgs bundles, and they have an obvious topological invariant, which you get from basically taking the Chern class or the topological invariant that determines the topological class of the principal HC bundle here, which lives in the second cohomology of X with coefficients in the fundamental group of H. Okay, so that's a G-Higgs bundle. That's exactly the definition also that Olivier and Steve showed you. And they have a modular spaces, of course. So here I included a little commercial break about why we should care, but I'm pretty sure that everybody in the audience already bought the modular space of G-Higgs bundles, so I guess I can do that pretty quickly. I just want to mention among there are many reasons for caring about this, many more than I wrote there. Just let me briefly mention one of them, which has of course also appeared, which is another Abelian-Hodge theorem, which tells you that you can have various incarnations of this moduli space as the character variety of representations of the surface group, as the moduli space of flat connections, or also a gauge theoretic incarnation as the moduli of what you might want to call harmonic bundles or solutions to the Hitchin equations. Okay, so I'll come back to the higher Teichmüller aspect a bit later in the talk, even though I will generally focus on the Higgs bundle point of view. Okay, so you have a topological space. You care about it. What do you want to know? You want to know topological invariance, and the most basic one is, of course, pi naught the number of connected components. So this question, from various points of view, has actually a long history. It's certainly been seriously studied, at least since the 1980s, with the work of Bill Goldman, but maybe even for longer. It's actually surprising, given what we saw, like in the talk of several talks, actually, for instance, in talk of Thomas, that how much is actually known about the moduli space of Higgs bundles. Especially for complex groups, but also for real groups. But nevertheless, the general question of determining the number of connected components is in fact still open, even after more than 40 years of efforts. Anyway, in the case of a complex group, the result of the answer is well known since '93 for semi-simple groups, and so that was actually a proof given by Lee using flat connections, and Oscar and André gave a proof for any complex reductive G using Higgs bundles. And there, this topological invariant C simply determines the connected components. So the connected components are indexed, labeled by the topological invariant C. Okay, and now for real groups, that the story is different. It's more complicated. So let me just give you the most basic example, which is the real group SL2R. So a G-Higgs bundle for this group has this very well-known shape. So it's a line bundle L basically, and the corresponding rank 2 vector bundle is L plus L dual, and the Higgs field has this often diagonal form, and the topological class is just the degree of L. The Milnor inequality says that the absolute value of the degree of L is less than or equal to G minus 1. For the non-maximal case, the corresponding moduli component piece of the moduli space is connected. The maximal case is slightly different. In fact, you have two G minus 2 components, all indexed by the square roots of the canonical bundle of X. So you may say, okay, this is an indication that actually C doesn't distinguish components, even though you may say, well, this is just because you didn't look at the adjoint form of your group. If you go there, actually, they all become identified, and they are identified with Teichmüller space. So this has been known since the 1980s. It's the work of Hitchin and Goldman. Okay, so this is maybe an example that something is going on, but not really conclusive. Okay, but let me now then go on, and I'll show you that this is in fact sort of the beginning of various situations where indeed C does not count connected components. They're written down here some low-dimensional isomorphisms of Lie groups, and so each of these ways of thinking of PSL2R or SL2R corresponds to actually a situation where this is not the case. Okay, so the first one, thinking of SL2R as a split real group. So Hitchin in 92, in fact, constructed special connected components. He called them Teichmüller components. They're now known as Hitchin components, by constructing a section of the Hitchin map. Just as a parenthesis, let me mention that the Hitchin map was actually generalized by Oscar and Anna and Ramanan to something called the Hitchin-Kosten-Rallis section for any real reductive G. Of course, it defines components only in this split real situation. So how does it work? Well, you take a bunch of holomorphic differentials, and Hitchin explains your way to construct corresponding G-Higgs bundles, and shows that this is indeed a section, and it gives you a connected component. So in the SL2R case, it's very easy to write down. So remember that the shape of the bundles was essentially this, but instead of any L here, we just take the square root of the canonical, and then our quadratic differential fits up here in that place of the Higgs field, and you get the parameterization of the SL2R Hitchin components. Okay. Now the Hermitian situation, corresponding to thinking of PSL2R as PSU11. So this was very beautifully explained, of course, by Olivier. So I'll be brief about this. But anyway, in this Hermitian situation, you have an integer invariant, Toledo invariant. There's the Milner-Wood type inequality, which I've written down here, which says that the Toledo invariant is less than or equal to the rank of the symmetric space times 2G minus 2. G is the genus of X, and this gives you the notion of maximal G-Higgs bundles for this situation when G is of Hermitian type. So just to give you the example of SUPQ, so could include, of course, the SL2R example we saw. Then we have a vector bundle which decomposes like this. This is what a SUPQ Higgs bundle looks like. The determinant of E is trivial, and the Toledo invariant is just twice the degree of E. So in the maximal case, as Olivier showed us, there's this general Cayley correspondence, which identifies the, I should say here, of course, that we should restrict to tube type situation. So then the maximal piece of the modular space, so the subspace of those G-Higgs bundles which have maximal Toledo invariant, is isomorphic to a moduli space of K squared twisted Higgs bundles for a different group, which is this Cayley partner group. And there's this explicit parameterization of the component that Olivier showed us. So this of course, this built on work that was done by these people here in various combinations over the years, looking at the various classical cases. But now this works in complete generality. So what's worthwhile here to explain again is that just as in the case of the Hitchin components, which are extra components not detected by the topological invariant, also here we get extra connected components because we now have here for this Cayley partner group, we have a maximal compact, and then that gives us topological invariants, which were not visible in advance. So again, in the SUPP case, so P equal Q is the tube type case. In the maximal case, this gamma piece of the Higgs field is in fact an isomorphism, and this then reduces your structure group to just the structure group of V, which gives you this Cayley correspondence, and the other piece of the Higgs field in the GC Higgs bundle just comes from composing the two, just as what we saw in the bracket of 5 plus and 5 minus. Okay, So that was the maximal case of the emission situation. Let me just say also something about the non-maximal case. So also this is something where Oscar has been involved a lot over the years in studying this. So the conjecture is that when C is not maximal, in fact, then the subspace of the moduli space with topological invariant C is connected. So this topological invariant indeed distinguishes components. This is known in some cases, not very many. Of course, the list of emission groups is not, or non-compact type is not that long, but anyway, the only case that's really completely known is the case of UPQ, or SUPQ if you want. So this is an old work of mine together with Steve and Oscar. Even though there were some few cases left out, which weren't completely clear, which had to do with the possible existence of components completely consisting of strictly polystable UPQ Higgs bundles. But together with Goten, more recently we ruled that out. The other case where things are known are, of course, in the case of SP2R, which is just SL2R, and in SP4R. So this is a theorem of Oscar and Ignasis from 2004. Also, slightly different proof of that also covers the case of PSP4R, was given by myself and Andre a bit later, using a wall crossing ideas that are sort of closer to this approach. Okay, so this question is open. It's a pretty difficult one. Some time has been spent on trying to solve it. But I think now perhaps the time is right for another attack at it. And I think even though that's probably been clear for a while that a wall crossing argument for some suitable principal pairs might work. So essentially emulating what was done for UPQ, which is easier because you're working with an abelian category of objects. Basically, you're working with triples or more generally with chains. But exactly the work with Olivier, with Brian and Domingo and Oscar is that Olivier was telling us about the variations of hot structure is probably an important input to this, in fact, because it will give you in principle the bounds on the region of the parameter space that where you need to go to where you hopefully can solve the problem, and then you need to make the wall crossing work. Okay, so let me go on to the last incarnation of PSL2R, so which was PSO 1,2, so the indefinite orthogonal groups. So for a long time, in fact, somehow the naive expectation was that the Hitchin components and the maximal emission case were the only situations where the topological invariant failed to distinguish connected components of the G-Higgs bundle moduli space. So that turns out to be wrong. And in fact, so Marta Aparicio, as Steve already mentioned, looked at this situation in her PhD thesis, and already at this point, in fact, there were some indications of some extra components. There were some also Brian Collier and somewhat later, in fact, parameterized some extra components in the case of SOPP plus 1, which do not deform to the corresponding ones for which are extra components, so which are not distinguished by the topological invariant. So this is what we see then also in the Hitchin and maximal components, that are these extra components. So retrospectively, you can see that in fact in my PhD thesis I did the case of SP4R, which has as its a joint group SO2,3. So Brian's work sort of explained that fact as being really an SOPP plus 1 phenomenon, not a symplectic phenomenon. So you might just have thought that, well, the symplectic group is actually both split real and emission symmetric. You might have thought it was because of that, but really somehow the real explanation is that it is an SOPP plus 1 phenomenon, these funny components you get in SP4. Okay, so then this team of people Martha, Steve, Brian, Oscar, and Andre. Recently, we then, in fact, cracked the SOPQ case, and we defined this sort of generalized Cayley correspondence for this group, which is a sort of hybrid version of both the Hitchin parameterization of Hitchin components and the generalized Cayley correspondence parameterization of maximal components in the Hermitian case. So it has some bunch of holomorphic differentials here, which are like Hitchin component-like data, and as the in this case KP twisted the moduli space of Higgs bundles for a different group, different orthogonal group. With this data, we parameterized an open and closed subset of the moduli space of SOPQ Higgs bundles. So it's a union of connected components. To count them, of course, you need to count the connected components over here. And we did the count in general, and there's a complete list, except for the case when the group is Hermitian, which in the non-maximal cases is not known. Okay, so now there are these various situations, and so the final or the next part of my talk is that I'll report on a general mechanism, which you can read about in this paper by essentially the same authors of the previous one, except for Martha, which is this notion of a magical nilpotent in a Lie algebra, or magical SL2 triple. So I'm going to explain to you first the algebraic idea, which is an idea in Lie theory, and then I'll explain how then all these three previous constructions of special components that I've shown you, how they can be in fact all rolled into this general kind of what we call a generalized Cayley correspondence, which is then parameterizes this sort of special components. Okay, so the starting point is then a complex Lie algebra. So just I've just here slightly changed notation because I didn't want to. So before the G was a real group, now it's a complex group because I'll need to distinguish some various real forms, and therefore it's more convenient to do it like this. Okay, so now G is a complex group, and I'll distinguish the real forms I'm looking at. But I didn't want to carry that around. It would be heavy in the earlier part of the talk. Okay, so let's take a nilpotent in our Lie algebra. The Jacobson-Morozov theorem says that we can complete it to an SL2 triple, which is just like an embedding of an SL2C in our Lie algebra. And in fact, this gives you an identification of nilpotents with embedded SL2Cs up to conjugation by G. So we can sort of, for our purposes, we can go back and forth between nilpotents and SL2 triples in our Lie algebra. Okay, so if you have the situation, we can come up with a couple of decompositions of our complex Lie algebra G. Since we have an SL2, it decomposes as an SL2 module. So here each Wj is corresponding. This is a direct sum of irreducible representations. So I've written them there. So we have this decomposition coming from SL2 representation theory. Of course, we also have just our element, our semi-simple element H, and that one we can use to decompose the Lie algebra in weight spaces. So we have this decomposition, and of course these two decompositions are in fact compatible just because H sits in the SL2C. I'm also going to introduce here a piece of notation, which is the centralizer of the nilpotent E, which is V. What is this? This is just the sum of all these highest waist spaces in each of the SL2 representations. So I made a drawing of it here. So here in the vertical columns are the pieces of the grading of the Lie algebra G, and the horizontal bits are the SL2 representations. So each dot is like an intersection of one of these pieces. Okay, and particularly here at the bottom, we have something we call C, which is just a centralizer of the SL2. It's just a trivial SL2 representation in there. Also, by SL2 theory, we have the adjoint action of the nilpotent F, which defines isomorphisms here as going down all the way. Of course, the adjoint action of E, also isomorphisms going up, etc. That's very standard. So we have this picture here, and then of our Lie algebra. And then we define a vector space involution on our Lie algebra in the following way. So it's going to be +1 here on the V naught, and on all these other highest weight spaces, we define it to be equal to -1. Okay, and then the idea is that you just when you go down with these adjoint actions of F, you just each time you go down, you change the sign. So I've indicated that on this here. So here, I put the sign of this vector space involution by the way it's defined. Okay, so and now I can define the key concept here, which is the magical SL2 triple, or the magical nilpotent, which is when this a priori, excuse me, when this a priori vector space involution is in fact a Lie algebra involution. So it means that it preserves the Lie bracket. So these are then the magical SL2s or nilpotents. So here's a couple of examples which are hopefully not surprising. So one is if you have a principal nilpotent, and the other one is the phi plus from the Cayley correspondence that Olivier was talking about. Okay, here's an important remark, which is the following: if we have a magical nilpotent, in fact, then it's even, which by definition essentially means that all these odd pieces of the SL2 representations disappear. So our Lie algebra, in fact, looks like this. All these red bits that were here on the previous slides, they have disappeared. Okay, so now what do we get out of our magical nilpotent? So the point is we get some real forms, and that is what's going to give us then the generalized Cayley correspondence, or this correspondence of Higgs quantum moduli spaces. Well, if you have a Lie algebra involution, you get a corresponding Titanic Composition. So you get a real form, and that one we call the canonical real form, and we note it by GR. Okay, so this GR is then the real form given by this Titanic Composition. So this is the first real form. I'll tell you about the other one in a bit, but first I want to tell you that we, in fact, in our paper, classify all magical SL2s, or better, we classify the complex Lie algebras which admit magical nilpotent. This is using the classification of nilpotents in real Lie algebras, and then that gives us basically a list of possible complex Lie algebras which or real forms which arise as canonical real forms of magical nilpotent. So here's the list, which is then the following. So there are split real forms, Hermitian of tube type, SOPQ, and then 4 quaternionic real forms. So these 3 first ones were, of course, exactly the ones where there were these already these different kinds of Hitchin or Cayley correspondence kind of constructions, and there's then in addition these exceptional real forms. And here is one point where we in fact see a point of contact with the higher technical theory. This is exactly the list of groups which admits what's called a positive structure. It's a notion which was introduced by Olivier and Navin a few years back in the context of the side of representations of the non-Abelian Hodge correspondence. Okay, so how are we now going to, in these cases, try to put all these previously existing constructions of extra components together. We are going to introduce another real form, which we call the Cayley real form. How does this come about? Well, I'll just I've written here with formulas, but I'm going to show you a picture in a minute, which is perhaps easier to digest. But anyway, here's the weight 0 piece of our Lie algebra. We had at the top, we had this C, which was the W0, and then we have further down, we have all these pieces, which we call Z2MJ, where this 2MJ is just the index on the representation. So that's what I wrote here. And one of the things we show is that the nilpotent of the SL2 is magical exactly when each of these pieces, in fact, bracket into this C. So that's they don't go into anything higher. And it is also true that in fact, if the indices here I and J are distinct, then these Z pieces commute. And almost all of the Z pieces are in fact abelian. There's at most one which is not one-dimensional and therefore just abelian. So we call this index, we call it C, and then there may be this Z2MC, which brackets non-trivial, and then that bracket goes into the C piece. Okay, so here's the drawing in terms of this picture of our Lie algebra. So what's going on is then that we have C down here, and then we have all these Z's they are sitting here, and most of these are one-dimensional, but there may be one here which is higher dimensional, and it brackets with itself and ends up in C. Okay, so what does this mean? Well, this means that if we look at, on the one hand, C, and then on the other hand, all these Z's that sit in higher pieces of the representations, we have a Titanic Composition, because these two pieces of the algebra satisfy the properties for that. We have all these abelian pieces, each of them a copy of C, and then we have the semi-simple pairs of the Lie algebra G naught here, which is then the C plus the Z2MC when it exists. Then we have this Cayley real form, which is the one simply coming from this Titanic Composition. So this is how we define it. So this is of course split exactly if C is 0. And we can then define the Cayley partner as the group, or the algebra, the real algebra, which we have here. Okay, so back to Higgs bundles. So now the Lie theoretic data of these magical nilpotent then gave us these two real forms: the canonical real form, which is the one which corresponds to the kind of G-Higgs bundles that we want to look at. So this is the GR, and then we have this Cayley real form, and we want to do the following. We want to take Higgs bundles twisted by this MC+1. That was exactly the index that corresponded to that representation, and then we want to look at Higgs bundles for this Cayley real form on the one hand, and then we also have all the pieces that sit on these abelian bits of G naught, which we gather over here, which are like this Hitchin section kind of data. And out of all this data, so the GCR twisted Higgs bundles and the holomorphic differentials, we want to build a GR Higgs bundle in order to construct this generalized Cayley map. Excuse me. So we need to, out of this data here, then, so here we have a holomorphic C bundle, right? This is, C was the complexification of the maximal compact of our GRC here. We have a Higgs field. We have to build out of this then, in a way I'm going to explain to you, an HC bundle and an appropriate Higgs field. Okay, so we have So I was talking about Lie algebras before. Of course, we have the corresponding Lie groups. So here's our G, which is now the complexification of our GR. We have that subalgebra C as a corresponding subgroup that integrates to a subgroup that sits in here. We have our, let's look at the adjoint case. So I'm looking at a PSL2C inside G, which corresponds to the magical triple. And inside there, we have corresponding to the semi-simple element H, there's a C star. Okay. Okay, so what do we need? So we have from our Cayley partner Higgs bundle, we have a principal C bundle. Okay, we need another piece, which is like what you also need when you construct the Higgs section. So we need this basic uniformizing Higgs bundle, which is the one I already showed you at the beginning. So I take here its frame bundle, and this one here is just the Higgs field in that. So okay, and what are we doing? So since we know that our group C and T commute, we can in fact out of these two subgroups of H subgroups of these two subgroups of H commute, so we can build an H bundle in a simple way essentially just by extension of structure group. So so it's like basically a kind of like taking a kind of a tensor product. So we get our H bundle, which is the first piece of data we need for building a GR Higgs bundle. And now we need to get the Higgs field. Okay, so the Higgs field in our GCR Higgs bundle has to live over on this piece. Which is of course inside the adjoint bundle of the corresponding G bundle. Because of the way that we know that both the H and the SL2C act, we get in fact a decomposition of our adjoint bundle here in the corresponding sub bundles which correspond to these sub pieces GJ of the Lie algebra, and now let's put some Higgs fields in then using these decompositions. Okay, so the first thing we might notice is that in fact, so we have a subspace of the Lie algebra generated by this nilpotent F, and if I take the corresponding line bundle associated via this frame bundle of the uniformizing Higgs bundle ET, we just get K-1. This is just sort of dual of the canonical bundle. This is just because of the way that the H acts on the adjoint representation, that this becomes K-1. So that means if we tensor by K, we get the trivial bundle. So that means we have sort of a trivial section like that one in the uniformizing Higgs bundle, which in fact lives here in the -2. In the -2 weight part of the adjoint bundle, and this is this kind of Higgs field we can put on, so that's the one that has the role of the one there. Okay. Moreover, we have all these highest weight spaces, and remember the way the magical involution was defined. These are actually all in M. So all these pieces of the adjoint bundle, in fact, are also M pieces, so they are places where you can put a Higgs field if you want to define a GR Higgs bundle. Okay, what would be the input? The input would be, in fact, the Higgs bundle for the Cayley partner. So maybe before I show you, instead of showing you this, it's probably better to just show you the drawing. Okay, so of how this construction works. Okay, so we have this F piece of the Higgs field in the GR Higgs bundle that we want to construct. We also, if our starting point is in fact a Higgs bundle for the Cayley partner, well, what do we have? We have pieces of the Higgs field which sit in these Z bits, right? But we want to go to the M bit of the GR Higgs bundle. And then what we're taking advantage is that we know that all these V's live in the M bit. So what we want to get is actually these phi's. And what's the point? The point is that we know that the add f are giving isomorphisms, so we can just go down here and get an isomorphism between this space and this space. Now the add f is in fact living there, so it has this twist by k. So this is why we can get these isomorphisms by just taking one of these phi's down to a psi by consecutively applying the adjoint action of f. If we out here want to twist by k, in here we get a twist by however many times we apply f plus 1, which is what's written there. Now, of course, we really want to get the other way, so the starting point of the psi's, and we apply, in fact, the inverse of this map to go from the Cayley partner Higgs bundle to the G-Higgs bundle. Okay, so this is how the map is defined. We proved that it's well defined, injective, and open and closed. So in particular, its image is like the previously known sort of Hitchin or Cayley constructions. It gives you a union of connected components which are in some sense extra and unexpected. So let's see, I have about 7 minutes. So just very briefly about the proof, we need to use our classification theorem. It's quite delicate, in fact, to prove that it's well defined in the sense that it preserves stability. So there's a more general construction which is this global fluidovich slice of Cayley and Sanders, which this actually is a particular case of, but one of the things we add to that is in fact that the preservation of stability. To prove the openness, we are using basically a local analysis of the map. We are sort of working with a derivative. The reason why that works, I'd like to also point out, is that since we have here higher twist, the deformation theory of these Cayley partner Higgs bundles is actually much simpler because the obstruction space vanishes. So basically, if you work in the configuration space, you can make the analysis work very, very nicely, and you can prove the openness like that. Finally, the closeness uses the properness of the Hitchin map. Okay, so let me now, it's a good time to just detour. So I've emphasized all the time the Higgs bundle point of view on these things, and this has been sort of my point of view, but there is a parallel story on the side of the moduli spatial representations, which I just want to very briefly mention, which of course I can in no way do justice to neither the story nor the people behind it in 2 slides, but just want to mention that there's this notion of Anasov representations from introduced by Leboury. Both Hitchin and Maximo representations are in fact Anasov, and also these positive representations I referred to, which are a refinement of the Anasov conditions by Garcia and Beanhead, and they classified the real groups admitting this kind of positive structure, and it's exactly, as I said, the list that we have of those that arise as the canonical real form associated to magical nilpotence. And then there's this idea of a higher type Miller space, which is then a connected component, which consists entirely of positive representations. They should have some nice geometric properties. I should also mention Fock and Goncharov, which many people are not being mentioned here, who should have been, but at least maybe I'll just mention this. So there's a different point of view also on higher type Miller spaces using cluster algebras that are behind. Okay, so about the higher type Miller spaces then, what we show in our paper is that in fact our Cayley components all contain positive representations. So this is essentially because we start with that uniformizing Higgs bundle, which, as you may remember, corresponds to the Fuchsian representation uniformizing the Riemann surface, and therefore it is a nice positive representation. Also, we prove that in fact there are no representations in these extra Cayley components that factor through a parabolic. And then shortly after last year, in the middle of last year, Garcia, Leboury, and Beanhead showed that, in fact, all positive representations are anosive, that the positive representations form an open subset of the representation moduli space, and that they are closed in the subset of representations which do not factor through a parabolic. So taken together, these results mean that, in fact, these components, these our Cayley spaces, they are unions of components, of course, but these are all higher tabular spaces. Let me also just briefly mention these two names, Albaida and Pozzetti, which for the orthogonal groups have in fact shown that the positive representations are closed without having to meet this condition. Okay, so that was the parenthesis on higher tabular theory. And in my last 2 minutes, let me try to generally say then, what would you expect after nearly 40 years to be the answer then? So who knows whether this is again naive, but anyway, I'll dare writing down as a conjecture that now we know that these mechanisms we've found should produce all extra components that are not detected then by the topological invariant. As evidence for this, you can say that in fact for the classical groups, this is now known by many years of hard work, except for this case I told you about close to the beginning about the non-maximal Hermitian case, which is really only known for SP4 and SUPQ. Okay, so in the last few seconds, let me just try to give you a brief indication about how this might be done using the C-star action that we've of course also heard about here during the conference. So this is of course also very well known, and given that I'm basically running out of time, I want to just give you the upshot. So what's the upshot? It's what's here at the bottom of the slide, which says that basically to count the connected components of the moduli space, what you need to count is the connected components of the locus of minimal fixed points of the C-star action on your moduli space. So this is the upshot of Hitchings' methods for counting components. Okay, so you have all the critical points, which are the variations of Hodge structure that Olivier told us about, and now you want to identify the ones that correspond that are minimal for the C-star action. So you think of the C-star action as giving you this flow and so on. Okay, so this is the story that was beautifully told by Olivier, and the basic tool then for finding the minima is this theorem from many years ago, but which looks innocent, but is really crucial and useful in this business. There's this condition which elevates a condition from deformation theory to actually a notion that you can just define in terms of properties of the adjoint action of the Higgs field on the adjoint bundle. So this is the condition for all negative weights. You get isomorphisms by taking the adjoint action of phi. Okay, so then, excuse me, the program is clear. You want to find all minimal Hodge bundles, and then you need to prove connectedness. Of course, this is all hard work. You have to worry about singularities, but anyway, the first goal is clear: find all the minimal Hodge bundles. Okay, and here's your tool, and then now you know in general theoretic terms that what you're looking for is looking for what came from this generalized Cayley correspondence. Hopefully you can do it. It has not been done yet, but we're trying. Just to give you one final result that is new, and which is maybe hopefully a step on the way, is that if we take some SL2 triple in our algebra, which comes with a Titanic composition corresponding to the real form, and let's assume then that the F, which we sort of would like to think about as the Higgs field of the minimum, right, that fits with the Cayley correspondence, in fact. Let's assume that for all the negative weights, so this is a lead theoretical result. Okay, I've written about bundles again. Let's suppose we have these isomorphisms that are coming from the criterion. Then, in fact, this triple has to be magical, and the canonical real form is the one given by G. Of course, this is not all you need, because this H doesn't have to be a grading element, and that's why you need to do some more work even in the simplest smooth case to find out what's going on, and it turns out to be in fact quite subtle, but this is perhaps hopefully a first step on the way. So this is all I had to say, so I'll stop here, and happy birthday again, Oscar, and many happy returns.
Okay, thank you, Peter. So is there any question or comment?
Thank you, Peter. Do you hear me?
I hear you, yes.
Good. Thank you very much. And I'm sorry that we are all sorry that you couldn't come, and we all appreciate the effort in giving, this talk via Zoom. But I just want to say that because you couldn't come, I will try to go and visit you as soon as possible.
Great, thank you. I'm looking forward to it.
We have to continue work, but to get some inspiration, I wonder if we can just go and get some of that wonderful octopus. Rivalia, yeah?
Yes, absolutely. I'll reserve it, yes.
You make sure.
Yeah, absolutely. Yes, yes.
Thank you.
Yes. That is guaranteed, yes.
Okay, is there any other comment, question? Yes.
Yeah, hi, this is Carlos. Maybe I missed this, but did you say what's the status for these quaternionic exceptional groups?
Yeah, no, I don't think I want to make a very definite statement. I mean, so there are some. I mean, you can certainly get the extra components, for instance, in the E6 and the F4 case. So you do get these unexpected, you may say, on higher Teichmüller space Cayley components, kind of components. I don't want to commit to saying that the count of components is in fact known. That would require a bit more work. I mean, because you do need to exclude the fact that you could find other minimum Hodge bundles, and we are not quite there yet.
Okay, thanks.
Okay, so any other question? So if not, let's thank Peter again.
Thank you.